Okay, so I will solve some problems on vibrations, and the first one is something like this. Let's say that you have a disk. Okay. So on one side you have a spring. On the other side you have a viscous damper, E, and on this side we have a K. This has moves with X, but it also rotates with theta, and X and theta are related, no slip here. And this is a disk with mass, and its mass moment of inertia is 1/2 mr squared. What is asked is the equation of motion is asked. And then there is some data is given. So this is what is it. First we will find the equation of motion, and then x of 0 is 0. That is, if we pull this thing 0.2 meters and leave it, what is the motion? Well, for the equation of motion, we will use the Newton's method. We can use energy method as well. They are equivalent. Actually, they are derived from each other. So, but this is more insightful. Let's say we draw the free body diagram of the disk and put the forces on it. Now, if this is x, there is the coordinate theta is here. Now, what are the displacements? What are the forces? I'm sorry. There is the mg force of the disk, which is not very important, but let's put it. There is the normal force of the disk. Well, there has to be a friction force, F. Otherwise, there will be slip. So there is the spring force, Kx. When x goes towards the right, Kx is towards the left. And when the x dot is towards the right, we have the x dot is also towards the left. It's opposite to x. Okay. These are all the forces on this thing. This should be equivalent to the virtual forces on this thing. Let me the circle. Okay. It should be the inertia forces mx double dot, and then you will have I theta double dot. You could have put, negative forces like here also, and then equate them to 0. That's another possibility. That is, we could put minus I theta double dot and minus mx double dot, and then equate it to 0, but it's the same thing. Well, theta double dot, theta double dot is alpha. Angular acceleration of the disk, okay? Change of angles. So we sum up the forces in the x direction. The spring force is kx minus bx dot minus the friction force. We don't know the friction force, but we will find it out. It is not mu times n or anything. Don't get confused about this. The friction force is not mu times n in this case. So this is the translational motion, translational equation. And then there is, we will take moments about this point O, let's say. Point O. Let's say that we will take clockwise as positive. In this picture, if you take moments about all the forces, none of the forces are moment except F. So it is F times R is equal to I theta double dot, which is equal to I is 1 over 2 mR squared. So this is the rotation. Okay. There is one more thing. This is not enough. Okay. We have one more equation, and that's important. It is because of no slip. We have x and theta are related. This is the no slip condition. I'm sorry. So it is the kinematics. And you can take the derivatives of this. X dot is equal to r theta dot. I'm sorry again. R theta dot. These are kinematic conditions. This is kinematics. This has come from the kinematics of the problem. We can, from here, we can eliminate theta or theta double dot. Theta double dot is going to be x double dot over r, for example. Okay. Now, one thing we don't know is f. F is unknown. So we want to eliminate this. F is equal to actually, what is it? F, if you divide it, mr over 2 theta double dot. A theta double dot is x double dot over r, right? So r over 2 times x double dot over r. R's cancel. So it is m over 2 times x double dot. That's interestingly, we get a simple expression. Now we can substitute it into the translational equation. You have an f term here. Okay. And you pass it to the other side, so you get m plus m over 2 x double dot plus dx dot plus kx. So you have an equivalent mass of 3m over 2, as you see. So our equation of motion is x double dot plus, if you divide everything by that, 2b over 3m x dot plus 2k over 3m x equals 0. And in our standard form, remember that we had x double dot plus 2 zeta omega and x dot plus X equals 0. So these terms correspond to each other. For example, the natural frequency squared is 2k over 3m. And then 2 zeta omega n is equal to 2b over 3m. These twos cancel, and we can write zeta is equal to, from here, b over 3m omega n. Omega n is the square root of this. So 3 times b over 3m square root of, it is 1 over omega n, so it is 3m over 2k. What do we get? We get a root 3 here, we get a root n here, b over the square root of 6. This is zeta. Okay, so we need to find the numerical values now. We can find the numerical values. The natural frequency is square root of numbers are given 2 times 7. This is, well, 1. And the damping ratio is 10 divided by from here. So 6 times n is what? Is the is something like this. So we find the natural frequency and the damping ratio. Well, since this is damped vibrations, we need the damped natural frequency as well. As you see, the damped natural frequency is very, very close to the natural frequency, which is 1, because the damping is very small here, as you see. And the period of oscillations is 2 pi over omega d. If you find it, it is 6.3 seconds. That is, one vibration takes 6.3 seconds, which is really long, by the way. Okay. All right. Now, if you have free vibrations, the general solution, as you might remember, is x0 amplitude e to the minus zeta omega n t cosine omega dt minus the phase angle. Okay. We also have the initial conditions. X of 0 is 0.2. X dot of 0 is 0. Okay, it's given. Any questions? Okay, but we have to find the result now. For what we have to find these actually. Find x0 and phi from initial conditions. So x of 0, which is 0.2, is equal to, if you substitute t equals 0, this becomes a 1, this becomes a 0, cosine phi. So it is x0 sine. Now we have to apply the initial condition to this thing. X dot of t, in general, we have to take the derivative of this, and it will be what? Minus x0 sine minus derivative of cosine is sine x0 omega d sine, not cosine. So it's taking the derivative of this. We take so x dot of 0 is equal to what? This is one equation, one. The second equation, minus x0, this is 1. Cosine minus 5 is 5. Cosine, right? Now, there's a minus here, x0 omega d. This is 1. This is sine, this is 0. Sine minus phi. Sine minus phi is minus sine phi. So it's a sine phi with a plus sign. And this will be 0. So x0s are going to cancel. Okay. This is because of the initial condition. Tangent phi, this will be, what would that be? Zeta omega n over omega d. This will be actually, omega d is zeta omega n over root squared. But zeta is already very small, okay? So this is in general true, but zeta, this is approximately equal to zeta actually. So tangent phi approximately equal to zeta, which is what, 0.0, oh, what was it, zeta? 0.06 something. So phi angle is 3.81 degrees. And cosine phi is actually it is 0.917. It's almost 1, okay? So at 0 is from equation 1, this is equation 2, by the way. At 0 is 0.2 divided by which is exact almost 0.2. All right, so we found the values. X of t therefore is 0.2004 e to the zeta omega n, which is 0.0 times cosine 0.t minus 3.81. So this is the result. Any questions about this? If not, I will solve another problem. So we have a bar here, which is hinged at 1/4 here, and there is a spring here, K. And on the other hand, there is another spring, that is 2K. And just in the middle, there is the damper. This is kind of similar to what we have in the Mach 320 vibration experiment, which you will be, well, we are seeing it now, I think. So, well, this thing vibrates, as you see, about this hinge point O. So it is like this rotation is theta. Okay, by the way, this is L over 4. This distance is L over 4, and this distance is L over 2 between D and the one end. On this disk, we have a external moment or torque applied M of T. Okay, I draw it with a different color. And M of T is, well, it is sinusoidal. M0 sinusoidal. So it is forced vibration, okay? Forced vibration, but forced vibration with harmonic forcing. Because sine omega t is harmonic, okay? Now, what is confusing is this is not translational, but rotational vibration, okay? This is a rotational system. The equations we have derived for forced vibration is valid, but you have to find their equivalents, and that is the challenging part here. And the data is as follows. The mass of this thing is 10 kilograms. The length L is 1.2 meters. This is a simple bar, so you can find its mass moment of inertia. L is that. K E. The damping is 650 newtons second per meter. And the forcing frequency omega is given. Omega is given in RPMs, 500 RPMs, okay? And we have to convert this RPMs to radians per second. That is important, okay? The conversion of units is important. And what is asked is the following. It's an inverted question in a way. Determine M0, the amplitude of the torque, this one, this thing, okay, so that the amplitude of vibration is less than 10 degrees. Yeah. So it is, well, a little bit, might be a little bit difficult. Actually, it takes a few steps here. First of all, we have to find the equation of motion. Then we have to apply all those formulas. If you want to find the equation of motion, as we said, there are two ways. We can use the energy method and the Newton's method for single degree of freedom systems. But here we will use the energy method. You might try using Middle method, if you like. Now we want to find the kinetic and potential energies. Now this is a rigid body, be careful. So the kinetic energy is not just 1 over 2 mvg squared. This is not just it, because this is a rigid body. In a rigid body, you also have the following term. This is translational kinetic energy. This is the rotational kinetic energy. Okay. Now, our bar is like this. It is hinged from 1/4 of it. So it is, and the G point, the mass center is in the middle, and the distance is L over 4, as you see. It is rotating with, if it's rotating with omega, omega, as you know, is theta dot, by the way. The velocity of the mass center is dependent on theta, since this is constrained. This is all. Vg is equal to L over 4 times omega, which is L over 4 times theta dot. Ig is 1 over 12 mL squared, as you might know. So the kinetic energy is 1 over 2 mvg squared, which is L over 4 theta dot squared plus 1 over 2. Ig, which is 1 over 12 L squared theta dot squared. So m is constant there, m is there, so it's 1 over 2 m theta dot squared is common in all terms, times L squared over 16 plus L squared over 12. 16 and 12. Common factor is 48 there, lowest common factor. So it's 4 and 7, 4 and 3 is 7. So it is 1 over 2, 7 over 48 mL squared. Okay, this is the kinetic energy of the system. We could have found it using, by the way, 1 over 2 I-O omega squared, okay? The kinetic energy about the fixed point. This is the mass moment of inertia with respect to point O. In that case, we would be using the parallel axis theorem, which would give us the same thing. So this is also possible. It would give us exactly the same thing. Okay, so we will find the potential energy now. Well, there are two springs, as we see here. One is here, one is there. This displacement of this spring is L over 4 times theta. This one is 3L over 4 times theta. So it is 1 over 2 in parentheses k times L over 4 theta squared plus 2k times 3L over 4 theta. And if you do the calculations, you get 1 over 2, 19 over 16, k L squared theta. So kinetic and potential energies are done now. Now there is the power dissipated. Dissipated power is the damping force times the velocity at the point where the force is applied, okay? So it is, the damping force is the power dissipated is but okay, let's not use minus. It is for the B times 4 times theta dot. This is the dissipation force times L over 4 theta dot. So this is FD, and this is V. This is B L squared over 16 theta dot. Okay, power, input power from the external thing is, it is M0 sine omega t. This is the power M of t times theta dot of t. Okay. Moment times the angular velocity. This is omega. Okay, now we have written all these terms. Now we can find out equation of motion, which is time rate of change of energy in the system is the input power minus the dissipated power. From which, and the energy is kinetic plus potential energy. Kinetic energy is there. We take derivative of this, the kinetic energy, and the potential energy. So what we get is 7 over 48 L squared. Maybe I shouldn't write this one. Let's write it later. This is dissipation plus the potential energy, 19 over 16 L squared theta times theta dot equals power in, which is 0 sine omega t times theta dot minus this derivative of this PL over square. And there is no derivative, sorry, this thing. 1 over 16 B L squared theta dot squared. As we see, we have theta dot terms in each of them. And this one. And when we collect the terms, we get the following equation of motion. 7/48 ml yes. So this is our equation of motion. This is our equivalent inertia, if you like. I equivalent. This is our equivalent damping. This is our equivalent spring. But we will divide everything by equivalent inertia, which is, by the way, we can calculate it. Seven over 48 times m is 50. Mass was 15 kilograms, right? Times 1.2. It was 3.15. But our equation can be converted to the following. If you divide everything by 7/48 ml squared, okay?
Hocam, M is 10 kilograms.
Really? Okay. Did I say that? I don't remember.
Yes, and you have to square 1.2 as well.
Huh? Oh, yes, that's right. That's right. Let me check just a second. And it's 10 kilograms, that's correct. So I don't know if this is correct. Let me just check. Probably it should be correct, but 10 times 1/2 squared. 1/2 squared is 1.44 times 10 times 7 divided by 48. It comes out to be 2.1 for some reason. Oh. Well, maybe should I modify the problem so that it's 15? Let me just see.
Hocam, it's 2.1 kilogram per.
Huh?
The answer for this is 2.1 kilogram meter square.
I know. How about if I change the original? The thing is, I made all the calculations according to 15, I think. So this might just create some problems. So if I do it 15, I think. Let me see.
Hocam, if you do 15, you get 3.15.
Yeah, so let's go up and change this to 15 kilograms, okay? So let's say I'll change this, and it won't be very easy. I don't know how to do this. Let's say that originally it's 15 kilograms. I think it's just a typo I made there. Because I made all the calculations I made are according to this one. So I guess I have to take a break, but one more step. Let's divide everything by 7.48 something. So our equation of motion becomes theta double dot plus. Now 7/48 is 3/6. 7 C over M or B over M.
Jam, you should probably change the 10 to 15 as well, just to avoid that error.
What?
Probably change the 10 in the I equivalent to 15 because you changed the mass up over there to 15 to erase any error. Thank you.
Oh, it is 57 over 7. K over M. Theta dot. Sorry, theta equals M0 over I equivalent sine omega t. So this is our equation of motion. We will use this in order to find our solution. We want theta of t, which is, let's say, theta 0 sine omega t minus 5. This will be theta 0 less than 10 degrees. Okay. So we want to find M0. But let's do that the next time. Let's take a break here because it's getting late. So let's pause the recording. Okay, let's continue while we start the recording. So this is similar to this following structure. Therefore, the omega n squared and 2 zeta omega n are as shown, and we can find omega n. K and M and B are given, so we can find omega n and zeta are found. Okay. Now remember, for harmonic forcing, we had x amplitude, x would be equal to f0 over k divided by square root of x. This is for the translational case. Okay. Now this omega over omega n happens very often. Let this call it R. So let's try to find this R. R is equal to, as we have said, omega over omega n. Omega is 500 RPMs, by the way. But RPM is not a proper unit. We want 2 pi over 60 to convert it to radians. 61.6 radians per second. And the result is 0.85. Okay. We are, not at resonance, but not too far from resonance either. 0.85 is kind of close to resonance. So this is for the translation, as we see, system. For the rotational system, this equation becomes let's call it x0. For the rotational system, theta 0 is M0 over K equivalent divided by square root of, but instead of omega over omega n, I will use R. As we know, 10 degrees, but we don't use degrees again. We use radians. Theta 0 less than 10 times 2 pi over 360, which is pi over 2 radians. So, well, here we have everything actually. So we want pi over 18 less than or equal to m0 over K equivalent divided by 0.85 squared plus 2 times 15 times 0.85. And if you compute this, this becomes 2.64 0 over K equivalent. And K equivalent, if you go back to our original equation, this is K equivalent, okay? In our equation. This is M equivalent, this is K equivalent. So this is 19 over 16 KL squared. So let's find it. K is so you have pi over 18 less than or equal to 2.64 and according to my calculations, it is M0 is should be less than or equal to 790.2 millimeters. This is the result. If you want less than 10 degrees, this is what you should have. Good. Well, Emir Teoman Bakır, we didn't look at these things, okay? Logarithmic decrement, etc., etc. We are responsible from whatever I have told, not from what I haven't told. So Okay. Another problem, probably this will be the last one. So we have a machine that is acted by a sinusoidal force. The machine is modeled by 1 degree of freedom system. So for this machine, we find that vibrations are, let's say vibrations. The maximum vibrations occurs at the period, forcing period of 0.22 seconds, and the maximum amplitude is 1.3 millimeters. And we want to find the equivalent spring constant of this system, K rather, not K equivalent, but K, and say the damping ratio for this system. First of all, omega, forcing frequency, omega is 2 pi over the period of oscillations, period of forcing, or period of forcing and period of oscillations are the same, 0.22. This is the resonant frequency, actually. Okay, this is where you have the resonance. So if you look at the frequency response curve for this system, this is R equals, let's say, omega over omega n, and this is 0 over 0 over k. It starts from here, 1, makes a peak, and then goes down. Okay. What we are really measuring is here, the maximum. R1, let's say, is omega resonant over omega n. So the resonant frequency is given as 28.6 radians per second. And we know that the resonant frequency is equal to not the natural frequency, but it is omega n times 1 minus 2 zeta squared, as we know. Okay. Therefore, this is known. Zeta is not known. Omega n is not known. And we can write the following. Omega n is equal to omega, which is omega resonant. This is over 1 minus 2 squared, or 28.6 over. That's one thing. Also, we know the following. Amplitude at resonance is x0 is equal to, if you remember, this is what we had found the last time, 2 zeta times 1 over squared. Now, what do we know? We know this, this is unknown, zeta is unknown. We don't know zeta either. But we can do something. We can kind of eliminate this, as you will see, the k from our equations. How? Well, we are given one more thing. Remember that we had omega n squared was k over n, so that k is equal to omega n squared n. So instead of k, we can substitute here f0 over m omega n. Squared. Okay, let me continue here. Omega n squared is the square of this, so omega n squared, actually, there's a square. X0 is equal to F0 and so what is unknown here? This is known, this is known, this is known. Omega is known. Only zeta is unknown in this equation, okay? So I can write this equation as follows. M x0 omega squared over x0 We will just put in the values, 25 times. X0 was supposed to be 1.3 millimeters, so it is 1.3 times 10 to the minus 3 meters times 28.6 squared. So this is an equation in terms of zeta. Which can be rearranged and to get a quadratic equation, you take square roots and everything, and you get the following: zeta to the 4 minus zeta squared plus 0.118 equals 0. So this is a quadratic in zeta squared. So it is quadratic equation in zeta squared, so it can be solved. Has two solutions. You know, the quadratic formula, etc. These are the possible solutions, but this one is not okay because if zeta is greater than 0.707, otherwise you won't have a peak in the vibrations. So this is the solution. This is the physically feasible solution. Okay. That is for zeta. Therefore, natural frequency we can find is 28.6 divided by root 2 times 6.9 squared. So it is 33.5 per second. And you see there is a difference. This is the resonant frequency, and this is the natural frequency. And the difference is not negligible between them because the damping is not very small here. But it is still not very large. Okay, why we wanted the natural frequency? Because we want the K value. K is equal to m omega n squared, as you know. From here, this is the solution. Okay. So this is what I have actually for solution. This last problem is somewhat difficult. Okay, it's not very easy to imagine this if you don't know what is going on. But I wanted to solve this. The one before the last is also kind of difficult. It's long, that is the problem. But you should be expecting, you know, some derivation of some kind of a vibrational equation of motion, and then doing something with it. And in all these problems, I try to do something like that. So, although I won't be asking something as difficult as the second or third problem, well, it won't be too very easy either, okay? I'm just trying to test your knowledge of the basic facts about vibrations, the concept studies. So, basically, today's lecture that's all for today. I'm going to talk about. If you have any questions, we might talk about that. Do you?
Jim, may I ask a question?
Yes.
Will the final be as long as the midterm was? Like, will it be 2 hours or will it be longer?
Well, it will, yeah, at least be 2 hours, maybe more, but at least it will be, well, it will be about 2 hours, yes. Well, I don't know exactly, but it will be about 2 hours, yes. I didn't decide on what questions, what kind of questions, how many questions, etc. yet. But I'll try to keep it kind of as, well, as short as possible, not a very long one.
Okay. Jim, are we, like, should we expect questions from the earlier chapters?
Every chapter, did you say?
Earlier chapters. Like
yes, yes. But except for the degree of freedom analysis, you can expect questions, yes. I'm not going to ask from degree of freedom. Okay?
Yeah, Jim. Jim, also midterm grades, I think, will be after the finals.
No, midterm grades, I am going to announce them today. Actually, I finished them, but I couldn't copy them to the ODTÜ class yet. I finished reading them. Probably I'll do it until the lunchtime or something. Okay?
Thanks, Jim.
Okay, you're welcome. So let me stop the recording also.